Hello, this is Kyle Welch with RCR Wireless News. I want to thank everyone for attending today's webinar, Furiously Fast Power Measurements, presented by Anritsu. Our presenter today is Russ Lindsay, Product Marketing Engineer at Anritsu. At this time, I'd like to pass the presentation over to Russ.
Good afternoon, everyone. Thank you for attending today's webinar. Today's presentation is Furiously Fast Power Measurements, Benefits of the Anritsu Universal Power Sensor Architecture. We're going to talk about this architecture in the context of an overall review of RF power measurements, and then get into the advantages of faster measurements and what to look for when buying a new sensor. So the reasons that you might want to measure RF power are common needs include design verification, regulatory compliance. For example, you may want to measure the RF power a mobile device is transmitting. System efficiency, you may want to measure the power being transmitted from a base station to make sure it's operating at peak efficiency for maximum capacity. Or safety, you may want to make sure that a component isn't going to be damaged with excessive power. So when it comes to the speed of power measurement, you're also going to see a big impact in automated test systems like calibrations or quality testing in high volume manufacturing lines. So for today's agenda, um, because RF power measurement is so important for so many applications, it's helpful to understand how RF power is measured. So we're going to start with an overview of RF power measurement, including a description of RF power and measurement types and measurement technologies. Then we'll do an overview of RF power measurement instrumentation with a focus on power meters, both traditional and USB sensors. We'll give some examples of features and functionality, and we'll spotlight some of the Anritsu microwave universal USB sensor technology. We'll talk about the confidence you can expect to have in your measurement and contributors to uncertainty. And then we'll talk about the impact of measurement speed, and particularly in automated test scenarios. So finally, we'll summarize what we covered and open up for any questions. So let's take this all the way back to the beginning with the basics of power measurement. So what is power? Power is a measure of the rate of doing work or transferring energy. In the electrical domain, the simplest case is DC, where power is simply voltage times current. When we're looking at RF power, though, we need to look at AC power, where it's still voltage times current, but now that voltage and current will vary over time. So in these equations for AC voltage, we see that the current will vary depending on the frequency and phase, should there be any reactive components in the circuit. So with our classic I times V, rewriting the equations and using some good old trigonometry, we arrive at the following equation for power as a function of time. So let's dig into AC power a little bit more. Let's look at some simple cases to get a feel for how power behaves over time. The instantaneous power to R in this diagram is still our voltage times our current as a function of time. In the case of a purely resistive load, voltage and current are in phase. So since the cosine of 0 is 1 and the sine is 0, this simplifies our power equation quite a bit. So we can see that the power delivered to the load will always be twice the frequency of the source, as represented by our 2 omega t, and that it is always positive. So to get an average power, we integrate we integrate our power over a period of time and divide that period by that period of time. Now be sure that you pick the right interval of the measurement of the sample that you want to measure. Typically select an interval such that your measurement time will allow you to capture hundreds to thousands of cycles. If you end up with some partial cycle out of the hundreds or thousands, it's not going to make a noticeable difference to your overall power measurement. For sinusoids, if we pick the interval to be an integer multiple of the period, the result is an average of 0 for the cosine term. So the average power delivered to the resistive load is P average is equal to the peak voltage times the peak current divided by 2. So we see a purely resistive, so now that's a purely resistive load. Let's take a look at a purely reactive load. So that was a purely resistive load. Now, in this case, this is a purely reactive load. The power delivered to C is still voltage times current as a function of time. In this case, the voltage and current differ in phase by 90 degrees. So to be specific, the current actually leads the voltage by 90 degrees. For a purely inductive load, the current would lag by 90 degrees. Again, we can do some simplification to our equation. Cosine of 90 degrees is 0, the sine is 1. You're left with simply the peak voltage times the current divided by 2 times the sine of omega t. Again, the resultant power is twice the frequency. However, in this case, P of t will vary around 0, both positively and negatively. And even though the magnitude of V and I haven't changed, when we average the power over one period cycle, the power is actually 0. That's because the capacitor is both storing and discharging energy. So let's go back to the general case. In general, the power being delivered to the load will be twice the frequency, which means that the power may be positive or negative. So you want to think of negative power as reducing the effective power delivered to the load, even though the magnitude of voltage and current haven't changed. So again, if we do some fancy math, the resulting effective or average power is given by your P average is equal to your voltage peak times your peak current divided by 2 times the cosine of the phase difference. Or we can rephrase that as VI times the cosine of theta, where theta is equal to your phase difference and V is your VRMS, which is your peak divided by the square root of 2. We notice that average power can be expressed in terms of RMS voltage and current. It's important to understand RMS. You're going to hear that term a lot in relation to power sensors. So what is RMS? First, we know the average value of the voltage and current waveforms over a cycle is 0, but obviously this doesn't tell us the whole story because there is power being delivered to the load. As a result, we want to give an effective value of the AC voltage and current of the waveforms, so sometimes referred to as the heating power or the DC equivalent power of the signal when applied to a resistive load. So here's what it looks like. RMS voltage is the square root of the mean being the equation which is shown in the bracket, of the square of the voltage or current waveform. So for sinusoids, it's simply V peak divided by the square root of 2. These equations will give you the effective power applied to the load. So now we have an understanding of power. Let's talk about how to measure it. Most commonly, power is measured with a power meter in combination with different types of sensors. The two most common sensors are diode-based and thermal-based. A thermal sensor utilizes a sensing device to measure the heating effect of the RF power. And with a diode detector sensor, the RF signal is detected or rectified, resulting in a DC voltage proportional to the signal's amplitude, depending on power level. In the first two techniques, the power is directly sensed. The RF is applied to a load, which converts RF to a DC quantity, which is measured by a meter. The direct sensing approach typically results in the most accurate power measurements. Now, people can and will use various types of receivers, like a spectrum analyzer or a vector signal analyzer, for example, to measure power. With this technique, the signal is attenuated and down converted to a band-limited intermediate frequency, where the signals can be amplified and filtered. The voltage amplitude is sampled and integrated to calculate power. The advantage is that the measurement is frequency selective, but it typically comes with the trade-off of being less accurate, or to be more specific, it actually has higher uncertainty due to the additional components in the signal chain. So in cases where the carrier frequency is low enough, a high-speed digitizer or digital storage oscilloscope can sample the waveform. For those of you who might actually want to see the full waveform. So we're more interested in the first two, so let's look more closely at sensor-based measurement techniques. We'll start with the thermal sensors. There are two basic types of thermal sensors. One uses thermistors and the other uses thermocouples. Thermal sensors using thermistors are called bolometer sensors. Usually bolometer sensors are based on a Wheatstone bridge, seen in the diagram here, where one bridge element is a thermistor. When the RF energy is applied to the thermistor, its temperature changes, so does its resistance. Circuitry adjusts the DC power delivered to the bridge to maintain balance. To change, or actually decrease, to be more specific, in DC power, that change is equal to the microwave power applied to the thermistor. This relationship is called DC substitution. Also, you'll see today in most thermistor-based sensors, they'll have a second thermistor, which is set to compensate for ambient temperature changes. Bolometer sensors were among the first type of RF microwave power sensors available. Today, they're primarily used in waveguide sensors and as standards in calibration labs. These sensors generally have the best linearity of the common sensor types. However, they tend to have the lowest dynamic range of common sensor types, somewhere from -20 to +10 dBm is typical. Bolometer sensors also tend to have low CW burnout or damage levels, around +20 dBm or so. At Anritsu, we currently use thermistor sensors as our working standards for calibrating our sensors. The second thermal-based technique for measuring RF power involves thermocouples. A thermocouple is a sensor for measuring temperature. It consists of two dissimilar metals joined together at one end. When the junction of the two metals is heated or cooled, a voltage is produced that can be correlated back to the temperature. For the purpose of the sensors, materials are chosen that will maximize V to make it easiest to read. The architecture is based on two scientific principles, the Thomson effect and the Peltier effect. Peltier found that junctions of dissimilar metals were heated or cooled depending on the direction in which the electrical current passed through them. Thomson predicted an EMF would arise within a single conductor whenever a temperature gradient was present. So the combination of the Thomson and Peltier effects are referred to as the Seebeck effect, which gives us the fundamental physical model for modern thermocouple detection elements. At Anritsu, thermocouples are used in our MA2400XA sensors. So the positives and negatives of thermocouple architecture. In thermocouple sensors, the output voltage from a thermocouple can be relatively low. For a T-type thermocouple, might only output 43 microvolts per degree C. So often multiple thermocouples are gained together to form a thermopile, resulting in higher net output voltage, which is easier to measure. Like thermistors, thermocouple-based sensors are fairly slow, with rise times in the millisecond range. As a result, they are not used to measure peak power or other fast phenomena. We will discuss peak power in a few slides. Thermocouples have a typical dynamic range of -20 or +20 to -30 or 35, which is a little wider than your typical thermistor-based sensor. They have very good linearity at low powers and good linearity at high powers. So typically, thermocouples have a good resistance to ESD, other transient burnout, making them more robust thermistors, more robust than thermistors. So for all the reasons above, thermocouple sensors are more common sensors for regular use than thermistors. Thermistor sensors are common for cal labs. So the challenge in general for thermal sensors is that they're relatively slow and have a limited measurement range. So an alternative that we mentioned was the diode-based sensor. Diode sensors incorporate a diode or diode pair to detect or rectify RF power being delivered to a precision load. The diode impedance changes with the power level. So for broadband designs, your matching load resistor will be 50 ohms to eliminate or at least reduce reflection. And it's important to understand how the diode characteristics change at different power levels. So diode behavior can commonly be broken down into three regions of operation. So below -20 dBm, diodes produce a DC output that's pretty closely proportional to the square of the applied voltage. This is what we call the square law region of the diode sensor. In this region, the average DC output voltage is going to be proportional to the average RF power. So even if modulation is present, so as long as the peak power remains in the square law region, this sensor can measure the average power of any signal type. In other words, it's modulation independent. Just be cautious of signals with high peak to average ratios or Crest factors. Be sure that the peak power remains in the square law region of the diodes at all times. You'll hear the term RMS sensors. These are designed so that the diode only operates in the square law region. On the right of the plot, above 0 dBm, the diodes go into forward conduction on each cycle of the carrier signal. At this point, the capacitor holds the peak RF voltage, so the DC output is proportional to the peak RF voltage. This is called the linear operating region of the diode. The RF power of a modulated or complex signal can be measured within certain conditions. In this region, the sensor is behaving as a peak envelope detector, which we'll go into that here in a minute as well. In between the square law and linear regions is the transition region. A lot of care has to be taken in this region to carefully characterize the diode behavior to properly capture the relationship between the power presented and the output voltage. It's much more difficult in this region to get an accurate power measurement. So which diode region should you use? The answer is that it really depends on what you're trying to measure. Diode sensors may focus on one or more regions of operation. A sensor with a single diode pair is going to use all three regions over its whole power range. Peak or wideband sensors are designed to keep power levels in the linear or transition regions. RMS or narrowband sensors are designed to keep power levels in the square law region. The one you use depends on the type of signal you want to measure. We can separate the type of signals into three basic categories: your CW mode, your CW waves, your pulse waves, and your modulated or combined signals. So for CW, it's pretty easy. You can really make a good measurement anywhere that the diode operates, the square law transition or linear regions. For pulse and modulated signals, we're going to want to dig a little bit deeper because it depends on what you're looking for. When we're measuring RF, you want to talk about the different type of power measurement terms that you might hear. If you're looking for instantaneous power, you want the sensor to operate the diode in the linear region. However, the ability to track the power will depend on how quickly the sensor can charge and discharge the capacitor. Even though diode sensors react much faster than thermal sensors, they may not be fast enough to recreate the waveform. In those cases, you probably want to use a high-speed digitizer or a DSO oscilloscope, as we mentioned previously in a previous slide. So in many cases, engineers are interested in what we call the peak of the envelope power, which is the amplitude change due to the modulation or distortion. Again, the diode should be in the linear region, and its effectiveness to capture the peak power envelope will depend on the rate of change of the envelope. Now, if a pulse is well behaved, in other words, the top is flat, the edges are sharp, you may only need to know the average power, where the diode performs the best in the square law region. Be clear, though, on which average you're interested in. For example, in the radar world, where pulse signals are often used, average has different meanings. Average can mean the average power over a pulse repetition interval. However, in some cases, of more interest is the average power only when the pulse or burst is actually on. Burst average power refers to the average power during the on portion of the pulse or the burst. Now, if the pulse is well behaved and the pulse width or PRI are known, an RMS detector can be used to calculate the burst average power by factoring the duty cycle of the measurement, which you can see in the equations in the bottom of the slide. So here the diagram shows the various types of RF power measurements you might want to compare and think about. So a second ago we talked about well-behaved waveforms. If a pulse is not well behaved, and or if you have other types of modulation in the signal, like in the digital communications world, an average or RMS sensor may no longer be sufficient. Similar to the pulse signal case we just discussed, it's unlikely one would want to measure the instantaneous power. Instead, they're probably more interested in the envelope power. To help conceptualize it, consider the diode detector circuit is actually functioning as a low-pass filter, where it's filtering out the carrier signal and leaving the modulation. In the plot to the right, you can see that the carrier waveform is filtered out, leaving the envelope power. When the term peak power is used in conjunction with a diode-based sensor, and a thermal sensor for that matter, it actually is describing the peak envelope power. Another factor to consider with a diode sensor is its ability to accurately capture the peak envelope power. This depends on whether it can respond fast enough or faster than the amplitude change of the modulation. A common measure used to determine the ability of the sensor to respond fast enough is video bandwidth. Peak sensors use a low impedance load across the smoothing capacitors to discharge them very quickly when the RF amplitude drops. This, in combination with very small smoothing capacitors, permits the peak power sensors to achieve rise times in the tens of nanoseconds range and corresponding to video bandwidths of tens of megahertz. So when looking at a pulse signal, like in our previous example, in order to capture the peak power envelope, the sensor has to react fast enough before the pulse is complete. One rule of thumb is the relationship between rise time and bandwidth is that the bandwidth is equal to about 0.35 divided by T of R, where T of R is the response time of the detection circuit. Now there is a trade-off for making the sensor faster or increasing the bandwidth. Going back to the low-pass filter analogy, while a higher pass band enables the sensor to respond to higher frequencies, higher frequency signal changes, the additional responsiveness makes it more sensitive to noise. So this is going to reduce the range of the sensor, whereas a sensor that may be able to measure power with a high accuracy, average power with a high accuracy at minus 60 dBm, it may only be able to get the same accuracy at minus 20 dBm when utilizing the full bandwidth. So here are a couple of points to keep in mind. So remember what we talked about, that the power meter measure the power of the RF envelope. So in essence, the amplitude modulation, they demodulate only AM at frequencies below the sensor video bandwidth. AM at higher rates will not be demodulated, meaning that the peak envelope power will not be available. Now, depending on the sensor, your average power might still be fine. And finally, remember that they don't see FM or code domain power, for example, or except for any effects on amplitude. So for example, the GMSK modulation example here, the amplitude is kept constant, so the measurement is unaffected, the power measurement is unaffected, unlike this QAM signal where modulation directly impacts its amplitude. So as is the case with most measurements, the measurement alone doesn't always give us the whole story. Once you have your measurement, how confident can you be in the result? It turns out that there are quite a few contributors to the uncertainty of a power measurement. Let's look at an example. Consider this example of an MA2472D standard diode sensor under the conditions listed. The uncertainty of the measurement is known as a plus or minus 4.89% or 0.207 dB under these conditions. And so here's our list of overall contributors to our overall uncertainty. From the chart, we can see mismatch uncertainty is the largest contributor by far in this specific example. So it's important to note that it's typically not the sensor viswar, but rather the DUT viswar that dominates the uncertainty element. If your test can handle a reduction in the measurement range, adding a precision attenuator of 3 to 10 dB can actually reduce the contribution of that mismatch uncertainty 2 to 10 times. In this example, noise, zero set, and drift are basically a non-factor. However, as the measurement levels approach the lower measurement range of the sensor, these will become more significant. So with as many contributing elements as we just showed you to uncertainty, it can be a little overwhelming to estimate the overall measurement uncertainty of your sensor or your measurement. Fortunately, many power measurement solution providers like Anritsu provide tools to help you estimate your uncertainty. Here are examples of Anritsu's measurement uncertainty calculators for traditional power sensor meters and also for the USB sensors, power sensors. So the user enters a few parameters describing the measurement setup, and your uncertainty is calculated for you. So now we've discussed some sensor types, both in terms of technology and measurement. Now let's look at how each of them might differ in measurement uncertainty. Let's take the same setup that we had earlier. The table below shows MUs for our 5 different sensor types. The top half of the table shows MUs under ideal conditions where the sensor and the DUT are perfectly matched, and the bottom half shows MUs for a standing wave ratio of 1.43 to 1. A few observations from the table, again specific to this measurement configuration. A single diode or diode pair gives the lowest uncertainty under ideal conditions. However, we can see that the diode-based sensors are much more sensitive to match with the DUT than the thermal sensors. The USB sensor and universal RMS sensors are very similar. The USB is a little better because the universal sensor has some added uncertainty associated with the reference calibration. Wideband sensor has the most uncertainty because its added sensitivity makes it more difficult to linearize, increasing the linearity contribution to its uncertainty. So let's discuss some basic tips. Remember, the quality of a sensor is reflected in its measurement accuracy. For power sensors, the achievable measurement accuracy is typically specified under the reference conditions. So consequently, it's very important to become familiar with the manufacturer's specifications and determine what additional error sources exist that can influence measurement. So again, here's some basic tips for identifying your measurement uncertainties. First, identify the type of signal being measured and the type of power measurement required. Select the sensor that best matches those needs. Determine the expected uncertainty of the measurement. Now, if the measurement is outside of the range of the expected uncertainty, you want to confirm that your test is properly set up. Are your connectors firmly tightened? Zeroing must generally be performed with the RF signal switched off or completely disconnected. Proper settings, have you set the RF frequency properly? If uncertainty is higher than desired, determine if the impedance match between the sensor and the duct can be improved. Again, like we mentioned, possibly adding a 3 to 10 dB attenuator, which could reduce the contribution of mismatch by 2 to 10 times. Now, even if you're careful when setting up a power measurement and have calculated out the uncertainty, there can still be surprises. For example, if you're trying to measure a single tone CW signal, you want to be careful or cautious of spurs. Because power sensors are broadband receivers, the sensor can't differentiate between the signal intended to be measured and other signals that might be present. So spurs in the AM noise floor can degrade the sensor's usable noise floor. Also, crest factor can be a factor that needs to be considered. Crest factor is the peak or peak envelope power to average power ratio. So many modern communication signals do have high crest factors. In some cases, they'll be 10 dB or higher. Pulse signals can have even higher crest factors, especially when the signal has a low duty cycle. So for example, if you're making an average power measurement, ensure that the peak signals stay entirely within the square law region. Otherwise, some peak power will be added into the average power measurement. Also, it's often the peak power that damages the diode sensors. Users have to be careful with the average power not to, while making average power measurements, do need to be mindful of the peak power levels. So even if the peaks aren't into the damage levels, if they're above the sensor measurement range, they can often degrade the accuracy of the reading. When making a peak envelope power measurement, peaks above 20 dBm, common top end of the measurement range for diode sensors, can be clipped and resulting in an inaccurate PEP measurement. Peaks above 20 dBm may be less of a factor on an average power measurement. It depends on the percentage of time the peaks are above the range. So the complementary cumulative density function, or CCDF, is a computation of the amount of the time the signal spends above the average power level of the measured signal. So many power measures include that CCDF computation as part of their feature set. So as a final note, you want to be careful when using seemingly benign accessories between your sensor and your DUT. For accurate measurements, you'll have to measure the insertion loss of anything you put in between the sensor and the DUT and back it out of the measurement. The insertion loss will have its own uncertainty, adding to the overall power measurement uncertainty. Even when making an insertion loss measurement on a high precision vector network analyzer like the Anritsu VectorStar VNA, you can still easily add 1/10 of dB of uncertainty to the power measurement. Be particularly wary of non-insertable devices, as they're difficult to measure and the associated uncertainty is difficult to estimate. A non-insertable device means that an adapter is required to connect the DUT to the power sensor. As mentioned previously, mismatch can have very significant effect on power measurement uncertainty. And just don't forget to consider the effect of any accessory added to the adapters on mismatch. So now you're all experts on power measurement. Let's talk a little bit about the architecture of power measurement tools that allow you to get the desired power measurements. In many cases, average power is of most interest. However, the square law region of one diode pair, perhaps a minus 25 dBm to minus 70 dBm, 45 dB of range, might not be sufficient to cover the full range of the device under test. Anritsu's patented the idea of using 3 diode pairs in one sensor, each operating in the square law region, essentially extending the measurement range to 84 dB or greater. In this example, the square law region is used in path A. In paths B and C, attenuation is added to attenuate higher input powers into the square law regions of the B and C diode pairs. The advantage of this approach is a wider range of modulation-independent RMS measurements. The challenge with this technique can include dealing with varying frequency responses of each detector, artifacts of ranging and switching between detector paths, or match complexities. If no modulation were present, that is if we were measuring a CW signal, a single diode pair would be sufficient. The Anritsu universal sensor is designed to combine the best of both worlds. So consider for a second an example where one would want to calibrate a transmitter using a communication system, used in a communication system. It may have to transmit many different signal formats depending on the receiver. For example, a cellular base station may have to work with 2G, 3G, and 4G mobiles. A common approach is to characterize the transmitter output RF signal chain with a CW signal at various power levels and frequencies. So a CW sensor will often provide the largest measurement range with the lowest uncertainty and without the trade-offs of switching between measurement paths. Those values are used to calibrate the transmitter output. When the calibration is complete, one will then want to verify the proper operation by transmitting test signals with different modulation formats. In the past, the test engineer would have to change the sensor to either a wideband sensor or an RMS sensor. That lengthens the test time and reduces repeatability inherent in disconnecting and reconnecting equipment. With the Anritsu universal sensors, an engineer can have the best of both worlds. In the universal sensors, there is a fast CW mode where one diode pair is used for CW measurements. In addition, with a simple software command, an engineer can switch to RMS mode, where three paths provide a wide range of average power measurement. So, moreover, because it's an RMS sensor, the average power can be determined regardless of modulation type. The highest measurement performance diode sensors require careful characterization. So, an example of a characterization system of a sensor is shown here. Suppliers like Anritsu will characterize their sensors over frequency, power, and temperature. Characterization over frequency produces what we call the calibration factors. Characterization over power and temperature, often called linearity correction. Data is stored in the sensor and used by the meter to correct for variations in the detector sensitivity. Typically, to apply the corrections, users provide the meter with frequency of the signal to be measured, while the sensor determines the temperature and power level. So we mentioned that a meter uses characterization data to correct for variations in the detector sensitivity. Let's talk about the role of a meter and what's currently available. Traditionally, power measurement instruments have been broken into two parts, the meter and the sensor. By keeping the sensors separate, they can be small. This enables the sensor to be placed close to the DUT, minimizing RF cabling. Sensors can also be specialized. For example, they can be thermal or diode. They can focus on CW, RMS, or peak measurements. Keeping them separate from the meter also allows the reusing multiple sensors for the same meter. However, a trade-off of keeping the sensors separate is that the user will have to perform a calibration to compensate for each different combination. We'll talk more about the traditional meters in the next slide. A more recent trend is to integrate the two, meter and sensor, into what's termed a USB power sensor. With these instruments, the meter is essentially built in with the exception of the measurement screen, so to display the data, the engineers will use a PC, or in Anritsu's case, they can actually use one of Anritsu's handheld instruments for the GUI. So power meters are essentially special purpose DC digitizers with an application-specific user interface. So they have high dynamic range and high resolution demands, which require gain ranging in front of the ADC. As signal levels get low, the reduced signal to noise ratio often requires a reduction in bandwidth for meaningful measurements. The low sensor output voltages at low powers require very careful attention to DC error sources in the amplifier. In fact, sometimes DC must be converted to AC. You may notice AC ranges shown in the diagram. Some signals can be so small that an incredibly high gain is required. However, very high DC gain amplifiers are much harder to build with low offset and 1/over frequency noise, as well as reasonable stability and bandwidth. It's really much easier to build an AC amplifier instead. So a chopper circuit is used to break up the input signal So they can be processed as if it were an AC signal, then integrated back into the DC signal at the output. In this way, extremely small DC signals can be amplified. The sensor provides the DC signal to be digitized, and a built-in EEPROM contains the correct data for the sensor. However, neither the sensor nor the meter can know the length of what cable is being utilized to interconnect them or its performance level. So to characterize the interconnect, that is to account for any wear or change in contact in the resistance, different cable lengths, DC losses, etc. The power meters are often equipped with a reference signal, typically a 50 megahertz source. So before making a measurement, the user would connect the sensor and its cable to the source to correct for any non-frequency related effects. So now let's compare that to USB sensors. Let's look at a typical architecture. You'll see here that they contain the functionality of both meter and sensor. Consider the block diagram shown here. Conceptually, it could be used to represent both a benchtop power meter slash sensor system and a USB sensor. In traditional power sensors, the signal the signal channel analog signal acquisition hardware, the preamps and the LPF, is distributed over three different components in measuring the system: the power sensor, the analog cable, and the power meter. Theoretically, it puts all three components at different ambient. So the 50 megahertz reference is required to calibrate for the effects of the ambient in this analog hardware, or simply put, to calibrate the effects of the analog cable. In USB sensors, the channel analog signal acquisition hardware, the preamps and the LPF, is integrated along with the RF front end of the power sensor into one small package. So you're reducing the connection of a 1.5 meter long cable to a few millimeters, and thus eliminating the need for calibration of this analog hardware. Along with the necessary frequency and temperature corrections which take place within the sensor, the USB will transfer calibrated / corrected data to in the digital format to the host PC or handheld. Some of the advantages: you have no additional time needed for reference calibrations. The sensor itself is smaller than a meter sensor combination and is typically less expensive than a meter sensor. The trade-offs is a USB sensor is typically larger than just a traditional sensor and typically more expensive than a traditional sensor alone, excluding the meter. So, and then finally, you do need, if you have a need for a display, additional equipment is required, like a PC or an Anritsu handheld. So, regardless of being standalone or integrated with the sensor, power meters offer a wide variety of features and functionality. So for CW signals, where timing isn't critical, one may just want continuous readings. For time-varying signals, one may want a graphical representation of the power with things like power versus time or profile plots. With that, you can do things like set limit lines. One can set up measurements to only measure power within gates and excluding fenced regions. Users can change the capture time. Oops, slide problems. There we go. For modulated signals, one may want to want a variety of power measurements like average peak envelope power and burst average power, or it may be useful to make some calculations or derive statistics from the measurement. The measurements may be triggered or non-triggered. Again, users can change capture times and sample rates or use presets from popular standards. So with a solid understanding of power measurement and the basics of meter and sensor technologies, let's spend the next several minutes talking about how we can speed up our test processes and with the appropriate sensor technologies. First, let's make the business case for speeding up measurement. The ultimate goal of a test system is to help the company make more money. Companies do that with better margins, by winning more business or bids, and by pleasing their customers to get return business. So how do we get from faster speeds to these three outcomes? First, obviously, faster measurements are going to shorten the test time. This is especially important in automated test scenarios like calibration or high-volume manufacturing. The shorter test times are going to lead to increased capacity, faster turnaround time or time to market, and decreased cost per unit. In the case of increased capacity, this happens because when you're testing more units faster, you're going to maximize your resource utilization You're going to minimize the amount of time a technician or other test equipment might sit idle while your power measurements are complete. This also decreases the cost per unit. And in this case, if your capacity is higher, you might be able to utilize less test equipment, which saves you capital expense and opens up floor space for building out other test systems to approach other business. It also means that the turnaround time from start to finish is faster. So when you go to bid on new projects, you can be more competitive from not only a time perspective, but also a cost per unit perspective. So all of these things lead us to, like we said, better margins, more competitive bidding, more business, and happier customers. Before jumping straight into faster test times, though, it's important to understand the trade-offs. Generally, you have three forces working against each other: speed, accuracy, and cost. So speeding up measurements is usually done in one of two ways, either taking less points or taking the same number of measurements in a short amount of time. The former method will decrease consistency and or accuracy of your test and diminish quality, but the latter is generally only achieved with more expensive equipment. Uh, Conversely, when you want to increase accuracy, which again is pretty much the same as quality, you're either going to have to slow down your test system or to take more points or spend more time in more money on higher end equipment. Now, at the bottom of our plot here, if managing costs is your priority, that may have to come at the expense of speed or accuracy or both. So with that understanding, let's talk about the factors that most affect measurement speed of power meters and sensors. So first there's calibrating and or zeroing the sensor. Like we talked about with USB sensors, one advantage is they don't require that calibration. But the zeroing is often required to set the sensor at a baseline. This can take upwards of 15 to 20 seconds per event. The next factor to consider is the number of data points that are averaged to obtain a final power measurement. Increasing the number of averages will minimize the noise factor in the measurement but slow down the reading. Decreasing averages will speed it up, but just as discussed, it will hurt the accuracy or consistency of your measurement. So finally, there's the actual measurement speed of the meter or sensor. This is the time elapsed from when a command or request is sent from your test system controller to the time that a measurement is received back. In an automated test system, this is happening extremely fast with a high number of data points, so increasing those measurement speeds can have a big impact on the overall speed of the test system. The diagram shows a simplified diagram of the measurement steps in a USB power sensor and how it would interface with an automated test controller. So if speed is your priority, here are the things you want to look for when choosing a new power meter or sensor. First, find one that has no zero required or zero can be done without removing from your DUT. Many USB sensors work this way and don't require calibration. Our 100 and 200 series USB sensors can be zeroed while connected to the DUT as long as the RF is turned off. Some sensors claim to allow zeroing even while the RF is on, which you just want to be careful about to ensure that there's no leakage, that your sensor is properly isolated from that RF signal. Another thing to look for is high accuracy in various environments. So if the sensor reacts well across its full temperature range, you're going to have a greater confidence when speeding up those measurements. Obviously, measurement speed is a specification you'll find in the datasheet. You want to look for fast measurement speeds, and of course try to find the thing that's most affordable without sacrificing that performance. One thing that we want to stress is that you really want to watch out for the fine print. Read the data sheets, especially the footnotes, carefully. Some sensors claim that they have extremely high measurement speeds, for example, but that may only be for a limited number of measurements, or it might be that those are unsettled measurements and aren't giving you a full quality reading. So now hopefully with that information and your now vast knowledge of measurement principles, you can pick the right sensor for your application. Of course, Anritsu has a wide variety of power meters and sensors that fit a wide variety of measurement needs. Last month we released the 200 series microwave universal USB sensors that are designed specifically with speed in mind. There is no zero required for signals above minus 45 dBm, and no need to disconnect from the DUT when zeroing. So as long as RF is turned off, they're very accurate sensors, not just at room temperature but across the entire temperature range. and have the highest overall measurement speeds of any USB sensor in their class. With Anritsu's industry-leading damage protection, your investment is also protected against accidental overpowering. Here are several of our other USB offerings. I mentioned our 100 series low-cost power meters, as well as our 105 inline sensor, which can be placed into the transmission line into an active transmission line, and can measure peak power. Our sensors are run by our free of charge Power Expert software that can be downloaded from anritsu.com. It's an intuitive interface with features of a traditional power meter and supports continuous average mode, scope mode, and time slot mode. All of these features are free with the download and don't require the purchase of upgrades. Here's an example of our Power Expert in continuous average mode. Here it is in slot mode, measuring a GSM 4-slot waveform. If you're looking to make a measurement of power over time, here is the Power Expert in scope mode. Another example here. Or you could also do a multi-sensor display to keep an eye on several measurements at once. We also have several benchtop meter options. Our 2430 series is our standard workhorse continuous wave model. We also, if you need modulated signals, you can step up into our wideband power meter, in the 2480 series. And if you're looking to do peak power measurements, our 2490 series will do so. We'll do those, of course, combined with the proper sensors. As discussed, we have the various type of diode sensors and thermal sensors, thermal-based sensors that will meet the need of your various measurements, a wide variety of power and frequency ranges. Our desktop meters can also be controlled via software for a more intuitive, easy to use user interface. Communicates to the power meter via Ethernet, runs on a laptop. They're compatible with our 2480 or 2490 series. You can do real-time view of measurement traces, multiple gates and markers, on archive and printing data for plots. And again, that software is completely free. So, in summary, we've covered a lot of topics today. We started with RF power measurement, with an RF power measurement review in which we defined and described RF power. We discussed measurement technologies by focusing on thermal and diode sensors. We examined different types, the different types of measurement and how they apply to various signal types. And we took some time to talk about the different type of instrumentation and how to choose that instrumentation based on the power principles we discussed. And finally, we went into measurement speed and the impact on test times. So I want to thank you for your time and joining us today. We look forward to working with you in any of your power measurement needs, and I'd like to open it up for any questions that you might have.
All right, Russ, thank you for that presentation. We have a number of questions that have come in, and again, I encourage everyone in the audience, please submit your questions via the control panel. All right, first question we received is, how does video bandwidth factor in when selecting a true RMS sensor?
Yeah, that's a good question. We actually get that question quite often. Important thing to remember is when you're making measurements with an RMS sensor, the video bandwidth is actually mostly irrelevant. You're just making modulation independent average measurements. The video bandwidth comes into play when you're trying to make peak power measurements. The important part there is that your sensor can react quickly enough to capture the full power of the pulse. If you're doing pulse measurements, for example. So in this case, if you're doing it when you're looking for an RMS sensor, video bandwidth is not something that you should be concerned about.
Unmuted.
Thanks. Next question we have is, when determining the measurement uncertainty, how do I pinpoint which factors are having the greatest impact?
So as we discussed earlier, the different factors that come into play with measurement uncertainty will vary depending on the type of measurement you're making. So when you're looking at a higher power measurement, for example, that's where your mismatch uncertainty is going to come into play more. That's why when we design our sensors at Anritsu, we work very hard to make sure that we are extremely careful and accurate in our matching protocols. And again, when you get into the lower measurements, that's when you're going to start to see a little bit more of that zero set and drift effects of the noise of your test signal, those kinds of things. So the important thing here is if you use the measurement calculators, the measurement uncertainty calculators that we provide, you can enter in all the parameters of your measurement and get a good confidence level in what your measurement uncertainties will be.
All right, thanks. Next question we had come in is, Power Expert, the software application you mentioned earlier, seems pretty intuitive, but can one person program the sensor directly for automated test?
Yeah, actually,
Muted.
that capability, actually, as a matter of fact, our new 200 series power sensors were designed very specifically with this high volume manufacturing usage in mind. So knowing that speed is a key factor in that case, they can be programmed
Unmuted.
using the programmable commands that way as well.
All right, I think we have time for a couple more questions here. So next one coming in is, you mentioned about the need to watch out for the fine print. Can you give a particular example of areas in which we need to be careful?
You know, the key with that one is when you're comparing across sensors, you really just want to make sure that you're comparing apples to apples. Measurement uncertainty is a good example of that. In some cases, when in a data sheet, one data sheet for a sensor might include things like the zero set and drift, and one might not. So the key is that as you are looking through the data sheets, that you look through the footnotes and make sure that you understand specifically what's included in each of the measurements, how long is it covering the full power range, those kinds of things, so that you're comparing, when you're comparing sensors, you're making sure you're comparing them correctly.
Okay, great. Next question we had come in is, you mentioned about USB sensors working with Anritsu handhelds. Why would a person need those, and don't the handhelds already measure power?
That's a great question. It's true that many of our handhelds do have the capability of handling power or making power measurements, but going back to our discussion earlier about the components that are included inside from the point of measurement to the point where you're actually making your measurement, there is some extra componentry within the handhelds that will add to your uncertainty. So using a sensor is designed to make that power measurement more accurate.
All right, great. Thank you. That's about all the time we have today. I want to thank everyone for attending today's webinar, Furiously Fast Power Measurements, presented by Anritsu. Again, our presenter today was Russell Lindsay, Product Marketing Engineer at Anritsu. Thank you, Russell.
Thank you.